Okay, here's a vital truth for your next technical interview. The way you actually choose to store a graph in memory, it literally affects every single algorithm you run on it. You could have the most brilliant traversal logic in the world, but man, if your foundational data structure is wrong, your code is going to time out, it's going to run out of memory, and yeah, it could potentially cost you the job.
So welcome to this explainer. Think of this as your ultimate playbook for mastering graph data structures for coding interviews. Whether you're tackling leak code for the absolute first time or you're brushing up for a senior role, understanding the fundamental differences between an adjacency list and an adjacency matrix is, well, absolutely non-negotiable. Today we're breaking down exactly how they work, when to use them, and crucially, how to build them.
Here's our roadmap for today. We'll start with the core concept, move into the adjacency matrix, then the adjacency list, build out a Java example, cover some common graph variations, and finally, deliver the interview verdict.
All right, section 1, the core graph concept. Let's make sure we totally understand nodes and edges.
Simply put, a graph is just nodes, which you'll often hear called vertices, connected by edges. Think of cities connected by highways, or, users connected by friendships on a social network. Conceptually, it's super intuitive, right? But structurally? How you represent that interconnected web in a computer's memory dictates the efficiency of literally everything you do next. Are you searching for a path? Counting connections? The time and space complexity of all those operations entirely depends on your storage choice.
Moving right along to section 2, the adjacency matrix, also known as the brute force grid.
Think of the adjacency matrix as a giant spreadsheet, or a 2D Boolean array. If you have 5 nodes, you just create a 5 by 5 grid. If there's a direct edge pointing from node I to node J, you mark that specific cell in the matrix as true, or maybe with a 1. No connection, it just stays false, or 0. It's highly visual and honestly very straightforward to conceptualize.
But here is the massive trade-off. Checking if node A connects to node B is instantaneous. We're talking a lightning-fast O of 1 lookup. However, look at that space complexity, O of V squared. If you have a million users with, say, 5 friends each, you're forcing the computer to build a grid of 1 trillion cells. That's like renting a massive 50-story skyscraper just to run a 2-person startup. Most of the grid is completely empty, which makes it a really terrible choice for real-world, sparse graphs.
So that brings us to section 3, the adjacency list. This is our lean and efficient champion.
Instead of generating a massive, mostly empty grid, the adjacency list takes a much more minimalist approach. For every single node, you simply maintain a list of its actual neighbors. If node 0 is connected to node 2 and node 5, node 0's list only contains the numbers 2 and 5. That's it. No blank spaces representing missing connections. You literally only store what actually exists.
And notice how the space complexity beautifully drops to O of V plus E, meaning the number of vertices plus the number of edges. You are no longer squaring your memory requirements. By only storing the nodes and the specific connections between them, the adjacency list becomes incredibly efficient for sparse graphs. And since interviewers absolutely love to test you on large, sparse networks, this structure is going to be your absolute go-to default for most coding problems.
Put simply, it's a battle of efficiency. The bulky matrix gives you those instant O of 1 lookups but taxes you heavily with O of V squared space. The lean list, on the other hand, sacrifices the instant lookups to save your memory at O of V plus E. In practical interview settings, protecting your memory is almost always the priority, which is exactly why the list takes the crown.
All right, section 4, building your Java example. Let's put this interview playbook into action.
Let's look at a classic interview question. Think of LeetCode 1971, find if path exists in graph. The prompt asks you to determine if a valid path exists between a start and end node given a 2D array of edges. But wait, before you can even search for that path, you have to actually build the graph. It's a 3-step process you really need to memorize. Step 1. Initialize a map where the key is the integer node and the value is a list of its neighbors. Step 2. Loop through every U and V edge pair in that given array. And Step 3. Populate the map by adding V to U's list. And, crucially for an undirected friendship graph, adding U to V's list. Boom! You've just translated a raw array into a highly traversable data structure.
Next up, section 5, graph variations. Let's talk about handling those interview curveballs. Remember, as we just saw, undirected means two-way streets. If A points to B, B points to A. But if the problem explicitly states the graph is directed, kind of like followers on a social platform, where I might follow you, but you don't necessarily follow me back, you only add the edge one way from source to destination. And what if they introduce a weighted graph, like roads with different distances? Well, you can't just store the neighbor's ID anymore. Your adjacency list needs to store pairs, the neighbor node alongside the specific weight or cost of traveling that edge. Adapting your course structure to these specific rules, that is exactly what separates a good candidate from a great one.
Finally, Section 6, the interview verdict. This is the golden rule of graph storage.
I want you to commit this quote directly to memory. Seriously, write it down. Always default to the adjacency list in an interview, pulling out the matrix only if instantaneous O1 edge lookup is strictly required. In, I'd say 95% of LeetCode style problems, the graph is going to be sparse, and your interviewer is going to be grading you heavily on space complexity. Start with the list. Make them prompt you for a matrix if they have a highly specific, dense graph edge case in mind.
So the big question, are you ready to optimize your next LeetCode graph problem? I really hope this explainer empowered you with the exact structural strategies you need to absolutely crush your next technical interview. Because now that your graph is perfectly stored in memory using an efficient adjacency list, a massive new question emerges. How are you going to traverse it? Are you going to dive deep with DFS or sweep wide with BFS? Well, that choice is your next step to mastering graphs. Go jump in, start coding, and I'll catch you in the next explainer.